So good morning all. So this is the experimental setup for four-probe setup. So so this is the four-probe setup. So 4-point probe is there. You can see the probes. So we can count number 1 from the left, 2, 3, and 4. Okay, number 1 from left, 1, 2, 3, 4. So basically, from 1 to 4, the current is flowing, right? And the voltage drop will be in the middle one, that is in the number 2 and number 3. And one silicon sample is there. Is it visible? So one silicon sample is there, already is put there. Okay, and it is connected with the probes. And this whole setup, this whole probe setup is connected with the microvoltmeter here and with the current source. So we have two current sources here. One is low current source. So it from 2 microampere to 2 milliampere is the range in this current source. So we have to choose a particular range, and by this knob we can adjust the current in that particular range. Okay, and this is the display, and it is in microampere or milliampere depending on the range we are choosing. And this is the current constant current source. So here the range is 20 milliampere, and from 0 of course, and to 200 milliampere. So we have to select. So this is the selector for this range. So if you select here, then it will be moving up to 20 milliampere. Then beyond that current, if we need more current, then we have to choose this selector to the right one, that is 20 milliampere. Okay, and here no microampere display will be there, is there. So in milliampere we will be getting the current. Okay, and here is the knob, we can adjust the current, we can increase in that range. Okay, this is the digital microvoltmeter. So here also the ranges are from 2 millivolt to 20 volt. Okay, so depending on the value of the voltage drop, so we have to choose accordingly. Okay, and this is the zero adjustment knob. So at the current 0, so what should be the voltage? It should be 0, right? But we'll see that if it is not a 0, then we have to adjust by this knob, and we have to make 0 voltage at the current 0. Okay. This is PID controlled oven. So here two ovens are there. One is oven 200 and one is oven 600. So first we have to select each of one. So this is the oven selector. So it is directed to the oven 200. So it will the temperature we can get from this oven up to 200 degree centigrade. Okay. Now if we select this one, oven 600, then the temperature we can get up to 600 degree centigrade. Okay, and why it is PID controlled oven? So there is a temperature controller here. There is a temperature controller here. So it is showing 20 degrees centigrade. So it is the present value. It is the present value of this setup of this oven. The temperature is 20 degrees centigrade, and below this it is SV, that is set value. Okay, so we have to set a particular value, and this will be the difference. It will calculate the temperature difference. It will calculate, and that differences they will execute through PID. That means proportional, integral, and differential. Okay, and then it will increase. The temperature will be increased at that particular rate. Okay, So and finally again the temperature difference it will calculate and it will be in the loop. Okay, so always it will calculate the temperature difference and accordingly they will change the temperature, they will increase the temperature in that particular rate. Okay, so now we are switching on the instruments. So we have to select, we have to use either of the current source. So for this silicon sample, so we will be using low current source. Now it is in the 2 microampere range. So the value would be now 0 microampere. Okay. And at that current, at that particular current, the voltage is now showing minus 0.046. Okay. So we have to do the zero adjustment here. Okay. So if we rotate anti-clockwise, then it is increasing. So we have to rotate clockwise to minimize it. So it is in 0 now. Now this display is visible because it is not growing. Is it visible? The display is visible or not?
Yes, sir.
Yes, sir. So we have increased the value of the current to 10 microampere. Okay, and then corresponding voltage we are getting is 1.293, and it is in microvolt region, right? It is in microvolt region. So the value will read as 1.294 microvolt, right? And we'll calculate the resistivity as per the formula V over I into 2 pi S. So V over I, that V voltage over the current 10 microampere into 2 pi S, that is the spacing of the probe. Okay, that will be rho 0, right? So we have to correct it by dividing the by G7 as per the value of the W by S. Okay. So again, we'll increase the current. We'll increase the current to another value, say 20 microampere, and it is showing one dot and nothing is there. So it is beyond the range of 2 millivolt. So we have to choose the next range, right? So after selecting the next range, the value is now showing, right? So the value is 2.67 microvolt now. Okay. Further we'll change the current. Say at 50, and the value is 6.68. In which value? In which unit? millivolt, right? Now we are changing the value 200. And the corresponding value of the voltage is 13.36, right? Further, we are increasing the value, say 150 microampere, and the value of the voltage drop is changing. Again, the range is, the value is beyond this range, so we have to select the next range. So now the value is 20 millivolt. So it will move up to 200 microampere in this range. So at say 195 microampere, the corresponding value is 26.1. Okay. So we have to choose the this selector of the voltage range in such a way that the value should be visible here. Otherwise, if it is beyond the range, if it is beyond the range, it will show just one dot and nothing will be there. Okay. So this is for the silicon. Now we are minimizing the current and we now change the sample. How to change the sample? So first you have to hold it, and by this screwdriver you have to pull it off. The setup, the 4 probe, you have to pull it off, and you have to be extra cautious while changing the sample. You have to safely remove the sample and keep it in a proper place. So this is the aluminum foil, commercial aluminum foil. You have to keep the sample beneath the 4 probe and gently release so that it touches it and strike it gently and put that in the oven. Now another current source we will be using. So we'll select this one. current is 0, and we have to do the zero adjustment again. So keep it in mind, we should wait for 5 minutes, but it will, but for the demonstration purpose only, we are not waiting. Okay. So we are using the 200 milliampere range and increase the current to 25 milliampere. So it is not in the micro range, it is in the milliampere range. Okay. And the corresponding value we have to note. So the value is 6.70 millivolt here. So there may be some calibration. We have to calibrate it to get the accurate value. So it is not calibrated now. Okay. So we'll see the how the experiment is performing for the demonstration purpose. So we have increased to 50 milliampere, and the value is now 13.64. And if we further increase to 100, the range we have to change. So it is 27. Okay. So for each current, we'll get some value of the voltage drop, and we can measure for each current the resistivity. Okay. And we can average out that. So we'll minimize this thing again. Okay. Now again we'll change the sample and we'll use now germanium. So this is the germanium sample. Again we will repeat the same procedure. Release it and remove the sample safely. We'll place the new sample. We have to be sure that it is coming below the 4 probes. Now we'll release it and tight it gently. So at 0, It is showing some value, so we have to wait for the samples to be stabilized. Yes, we can use the low current source also. So we'll choose low current. And let's see. So we have to do the zero adjustment again. Okay. Now we have to select a particular value of current here. So it is in 2 milliampere range. Okay. So we are choosing 1 milliampere. We are choosing 1 milliampere. And throughout the experiment, now we'll not disturb the current. Okay. And now we'll increase the temperature through this PID controlled oven and see how the voltage is changing. Okay. So now the temperature is at 22 degrees centigrade. Okay. So you can get some slightly different value from the corrected one uh, due to the calibration, due to the lack of calibration rather. So now the set value is 35. So we can change this. Okay, we can change this by this now. So if we have to change the value in this decimal, so we'll choose the upper part and it will be increased to 35, 36, 37. And if we have to change this decimal, so not decimal, this place, then we have to select that. So it is now blinking. So 3 is now blinking. So this one will be changing by this knob. And if we have to increase it, then we have to choose the upper key. And if we have to minimize it, then we have to choose the lower key. Okay. So if we choose the lower key, it will be now 27. And if we choose the upper key, then it will be now 37, 37, 47, 57, right? So we'll be choosing 35 now. So 35. Is it visible? Now,
Yes, sir.
okay. Now we'll switch on the oven. So this is the button for switch on the oven. Okay. Now we have to wait, and while it will be increasing, we have to note the temperature and corresponding the value of the voltage. So in one experiment, in dielectric constant experiment, there was also a set temperature, but the temperature was not mentioned there. So how to choose that upper part, the set value, that was not mentioned in that setup. So here you can control with yourself by putting the temperature you want to increase. So now it is 23 now. Okay. So it was 22, right? So it is increasing. Now it is 24. So if you choose the 45 in place of 35, so the rate of increase of temperature will be more. Okay. And if you choose the less difference, that is now it is 25, if you choose a 28, so it will not increase that much in that much rate. So we have to note down the temperature and corresponding voltage, because the current is, we are not changing now. So for that particular temperature, we have to calculate the value of resistivity, that is V, that value, over I, that is the constant here we have chosen, and into 2 pi s, and we have to divide by the geometrical correction factor. So the temperature is increasing, right? And the oven is switching on and off as per the controlled oven. Now it is 31 and the value is changing, and it has changed to 99.1 now millivolt. So it is increasing very fast now. So can you see the temperature and the voltage display simultaneously? So the temperature has moved to 37 degrees centigrade, and the set value is 42, and now the value is 95.4 millivolt. So we have to plot the resistivity over 1 over temperature, the temperature inverse, and from that we can get the value of the band gap of the sample we are using. So the now value is 40 and set value is 42. And you can see the change in the voltage. So the temperature will further increase, though the set value is 42 because of the thermal inertia. Now we'll be changing the value of the set temperature. So now it is 52. So it will take time. You have to take at least 130 degree temperature or so. So I think you have understood the procedure and how the experiment is executed, right? So we have to keep changing the set temperature, and accordingly that through PID controlled oven, the temperature will be increased as per the difference we are choosing. Okay, then we are closing the session. Thank you.